talking briefly about the ELF format. It's actually pretty similar to the one on x86, but I just thought I'd cover it here briefly. I'm sure this is also covered in the Life of Binaries course. So if you remember, ELF stands for Executable Linkable Format, and it essentially has this is what it looks like. So you have an init section, text, RO data, VSS, symbols table, and then you have some debug symbols down at the bottom here. If you remember the -G GDB option for GCC, this is where it generally puts all the debug symbols. And then it also has a string table for additional debugging. But the most interesting pieces are up at the top. You will have a read-only code segment. This is actually the stuff that gets loaded into memory, followed by the read-write data segment. So I'll talk a little bit more in detail about that. So then the .text section in the ELF, your binary, is essentially what has your code, the opcodes that the ARM processor actually acts on. The RO data is your read-only data section, so things like constants, things like that are put in this section. So if you remember our Hello World program, the .ro data section in your object dump, you would see the Hello World string located in this section. The .data has your global static variables. The .bss has your uninitialized variables. If you just say int a and don't initialize it, sort of sticks that variable in here. The heap actually in memory starts after the .bss section. So if you remember, I said that this segment actually gets put into memory. And once that gets put into memory, your heap starts right after your BSS, and it actually grows towards increasing memory. The stack actually starts at the opposite direction and starts growing towards the heap. And so the stack and the heap sort of meet in the middle, if you will. So the stack grows towards lower memory addresses, the heap grows towards increasing memory. All right? So again, a reiteration of the format. So if you remember, the debug section is actually where all your GDB symbols get put. The .line is, again, for more debugging. It puts in your line number, so when you say breakpoint at line number, it looks up the stuff in this section. There's another GDB command, actually, called list, which actually lists your program code in C when you're debugging. And the other thing that Galen mentioned, and a lot of people had questions on, was how to step over an instruction. So if you have an instruction that branches with like a branch instruction, and you didn't want to actually go into that piece of code, you can actually use an instruction called the next I, which essentially steps over that branch instruction. It doesn't branch, or it actually goes, executes that code, comes back, and then continues with the next instruction. Does that make sense? So there's next and next I. So they'll be more useful as opposed to putting a breakpoint at the instruction right after the branch and then doing continue. So that's the way I've been doing it. And your string table has all your symbol information, like variable names, things like that. So it's also used for more debugging. So now we'll start talking about how we can do a control hijack on ARM. So as you know, we can, if we're allowed to write to the stack pointer, you know that the link register usually gets saved onto the stack. So if you're able to write into the stack, you can control the link register at least. And when the code returns, the link register gets copied back into PC, and you can sort of control the flow of execution from there. The other thing to remember is if you, we talked about the ARM thumb procedure call standard. And the ATPCS specifies that R0 through R3 are used as arguments to methods. So if we wanted to pop something like a shell on a server or something, then we would have to make a system call or an exec-VE call, but we'd also need to pass arguments. So this is sort of, we're going to talk about how we can pop a shell. That's like the ultimate goal. So this is the picture I had shown you a couple of slides ago on what the frame looks like in your stack. So the callee save registers are first pushed on using the STMFD stack pointer with write back, and all the registers that you want to save are put in there. Followed by that, we have the link register, right? The link register is where the calling method's PC is saved. So that also is put on the stack. So the idea would be you would write, or if you're able to write into the stack, you're able to overwrite this address here, right? And when the function returns, it copies the link register back into the PC, and you can start, if you control that address, you can essentially have it execute arbitrary code. So this was an attack that was demonstrated, I think a year back, 2011 actually, by Itzhak Abraham at DEF CON. So if you remember, we can control the PC, but we can't control the arguments. How are we going to write /bin/sh as the argument to system into register R0, right? Because system expects an argument, and it's going to expect the argument in the register R0. So the only way to do it, at least his approach, is to use return-oriented programming. So what you do is you essentially point the link register on the stack to a piece of code that loads other values from the stack into your registers that you're interested in, right? And once you're able to do that, you can actually make a call to the system, and then R0 should have the argument to the system call, and then it should pop a shell. So the approach that he used was to use a piece of code from ERAN48, which is a libc function, and I'll show that to you graphically here. So the idea is, if we have a vulnerability, so in this case, I'm just taking a buffer, right, and whatever I'm expecting some sort of string input, I save that into a buffer, right, and then I return. I print it and then I return. So if you wanted to overwrite this buffer, you would actually have a buffer overflow vulnerability here. So you'll be able to write onto the stack. And then once you're able to write onto the stack, you put the address of ERAN48 as your link register value. And this actually ends up pointing to a piece of code inside ERAN48. Because the specific instructions that you want are to load values from the stack, since you control the stack, to be loaded into R0 and R1. And the instructions that he highlighted were these ones. So it starts off with LDRD R0 R1. So LDRD stands for load into register double. So it loads two 32-bit values into R0 and R1 respectively. Once it's done that, then it subtracts stack pointer minus 12, so it changes the stack pointer, and then it pops the link register into PC. So I actually didn't complete that, but it's just pseudocode. So once that happens, what will happen is if you are able to control buffer here, you're able to write to the stack, you're able to write the link register as ERAN48 plus X, and I'll show you how to do this. And then you're able to pass in the argument for R0, which is the string /bin/sh, But we have to put this string somewhere, right? So the way I did it was, we can actually do it two ways. You can put it in as part of your input string, where it gets put on the stack, and then you figure out where that address is, and you put that address as your argument. Or you can actually put it in an environment variable, you know, on your emulator, and you can actually reference the address of that environment variable and use that for R0 here. So either of two ways will work. So once you've put the argument for R0, what's going to happen is, so assume it's executing the vulnerable function. It's going to write your string onto the stack. Again, this is increasing memory. So it's actually, the stack will grow downwards, and the string gets read in reverse order, so it'll get put down this way. So once you have the link register pointing to this, what will happen is when it pops off, if you remember from our stack here, once it pops off this link register back into PC, it's going to jump into ERAN48 plus X, and it's going to load LDRD R0 R1. So it's going to take this value, put it into R0, take this value, put it into R1. Then it's going to subtract stack pointer minus 12, so it's going to actually jump to here. That's three 32-bit values, right? So that's decimal 12. So it's going to skip all this stuff and update the stack pointer to here. And then it's going to pop the link register again back into PC. So this is the ERAN48 code that's doing this. So you're going to have the address of system here. So at this point, R0 and R1 are going to have the arguments to your system. And finally, once you pop the address of system back into PC, it's going to make a call to system with the argument being the /bin/sh string, right? And here you can, here in this example, I'm just putting this /bin/sh string at the end. So once you're able to do this, you will have a shell. So this sort of leads it into lab 4, which is actually in your Linaro simulator. So you actually start up the Linaro simulator. Share this. And the approach I would encourage you to use is GDB. So you can actually step through the vulnerable code. So if you go into CD projects, B overflow, so you'll actually have boverflow.c. So this is just simulating a vulnerable piece of code. So there's just a car buffer of length 5. And it takes whatever input you've given the arguments to the program and calls a string copy into the buffer without checking the bounds. So, so this way you can actually, so you say overflow. It's just going to copy it into the stack. So the way to start doing this is actually, so to craft your input, you will need to use Perl. So let me go over that. So Perl should be installed. So what you can do is you say Perl-E, and you can do something like So each character is 1 byte, or sorry, yes, each character is 1 byte. So you're going to have 4 bytes, 32 bits on the stack, right? So you can have something like ABCD, and if I say times 3, let's go. Actually, I'll put that into a file. So actually, this is the format, sorry. So you do Perl-E, right, followed by a print, and then you give you can either give a hex code, or you can give arbitrary jump values. And X3 just repeats ABCD 3 times in your input string. And the way to concatenate these strings is you use period. So when you say Perl-E print ABCD times 3, it's going to print ABCD, 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 followed by hex of ABCD, DE, EF, and then concatenated with EFGH. And so you can actually run gdb.deoverflow and then breakpoint at stage 1. And once you've put your crafted string into solution, you can just say run. And then in backticks, you say cat solution, so it just outputs the Perl string in place and runs the buffer overflow program. So the idea here is you need to craft a string that will pop a shell. And in order to get the value, so if you want to look at what's in ERAN 48, what I suggest you do is, let me show this to you. So this slide is actually very useful for that. So what you can do is you can say GDB overflow. So now that's in GDB, you can actually breakpoint in main for now, and you can actually say P for print, ERAN 48. That's right, I gotta run this, so we'll run it with it. So you actually need to run the binary in order for the libc to actually get loaded, I guess. So now I've put a breakpoint in main. I've run it with some junk string, right? So once I'm there, I can actually print ERAN 48. So this actually gives you the address of where ERAN 48 is located in memory. And since it's a shared library, it's always around. You can actually disassemble ERAN 48 to look at what instructions are there. So this is what ERAN 48 looks like. And if you remember, the instructions of interest start off at this address, which is 76F28E56. It has the LDRD R0R1, and it's loading from the stack into these 2 registers. It's adding stack pointer plus 12. And then it's popping from the stack into PC. So these are the instructions of interest. So we want our link register to point to this address, right? And remember, everything here is in Little Endian, so you're going to have to provide this address in reverse. And one more very important thing before you start debugging that I should have put on this slide. Yes. So you want to echo 0 into randomized VA space. What this is this is a feature to prevent, this actually was meant to prevent these style of attacks, but it's address space layout randomization. So Linux actually randomizes where it puts the heap and the stack, depending on the value in this file right here. So there's actually 3 settings. There's 0, 1, and 2. I believe 2 randomizes heap and the stack, and 1 just randomizes the stack, and 0 doesn't do any randomization. So we want to turn off randomization because it helps us predict where these addresses are going to be in memory, for the stack especially. And since our string is also going on the stack, in my example anyway, it'll make it easier to pinpoint where that string is. So we're turning off address space layout randomization with that command up there. So. And if you want to make sure that 0 is being stored in there, you can just tap that value. So it should be 0. So I've been able to get this to work in GDB, but when it's not running GDB, it's kind of difficult to get it to work. So the exploits are in because the addresses are different. And the other thing also to remember is, you remember the ATPCS convention I talked about, where all addresses, you have to set the least significant bit of every address to 1. So whatever address you're getting for ERAN 48, you have to set that least significant bit. So just make it odd, essentially, add 1. So you can also look at your stack. So if you run in GDB, if you do run with a garbage string like ABCD to LMNOP, you can actually see where it ends up in your stack. If you just do examine/5s stack pointer or stack pointer minus 12, you'll see exactly where your string ends up. So if you need to reference this paper, there's a folder on the desktop called Red2ZP. It has an actual paper for reference. So for this lab, I actually want to credit Zeno for finding out the mode switch issue, where you have to set the least significant bit to 1. Actually, so we can break for lunch now. Also on the system call, so wherever you're doing a branch, basically, you have to do, because if you see the ATPCS manual, so if you go to section 5, like 1, please. We use the branch exchange. Simultaneously change instruction set to that specified by the least significant bit of the destination address. But the interesting thing I also found out is my make file for the B overflow uses the -m arm option. So even though I'm saying compile it in ARM, it doesn't work. So that's why you're always seeing thumb code for all my examples. Is if I try the -m ARM option on the emulator, for some reason GCC is not producing ARM code. It's still producing thumb. The way you can see this is if you actually do object thumb -d b overflow OS, you'll actually see some of it. You'll see the intermixing between 16-bit and 32-bit codes. So actually, the main is all 32-bit instead of state 1. It's just that the shared libraries like libc is going to be mixed. So you're going to have like the libc is going to be mostly in thumb, but your main and stage 1 actually are in. If I change this to m thumb, so now if I do thumb, you can see that main and stage 1. So it's actually working. So you can see that it's now producing mixed 16-bit and 32-bit codes. So working for me. But the libc is always going to be in thumb, because that's an artifact from the Linaro image that I downloaded. So if you compile the voverflow in thumb, you might not have to add that one to the address. That was a good question. Yeah, so even if I put it in thumb mode, you still have to add that one.